Now that we're able to write out these equations in a couple of different forms, which form you pick kind of is dependent on what you need to or want to do with your reaction, right? So what kind of problems do you want to solve with that? Do you just need to figure out what the precipitate is? Do you need to figure out how much mass of stuff? Do you need to do some stoichiometry? And so, yes, we absolutely 100% can do stoichiometry problems for a reaction in solution. So what we'll do, our steps for this are, identify the species that are present in the combined solution and determine what reaction, if any, because sometimes you got no reaction, occurs. And then you're going to write out the balanced net ionic equation for the reaction. We kind of don't care about the spectator ions, right? They're not involved in our chemical reaction. They're not part of our product. They're not a reactant that is actually changing, so we just need the net ionic equation. We can then calculate the moles of reactants, determine what the reactant is limiting, calculate the moles of the product as required, and then convert to grams or other units as required. So once you get to the only difference between this and what we did in the last chapter is that it's happening in a solution, and instead of using the full molecular equation, we only need this net ionic equation. Right? The steps to do limiting a reactant, the steps to find out how much is left over, the steps to find out percent yield, those are all the same as any other reaction that you would have done in your stoichiometry chapter. All right, so let's do an example. We have 10 milliliters of a 0.3 molar sodium phosphate solution that's going to react with 20 milliliters of a 0.2 molar lead nitrate solution. So again, step 0 is going to be balanced chemical equation. Your second reflex is get it into moles. If you see grams of something, get it into moles. If you see a volume and a concentration, that's just moles hiding out as a liquid, right? Here we got a concentration and a volume. That's going to give us moles, right? So your reflex is going to be balanced chemical equation, right? Step 1, find the moles, right? In here, we're going to look at our balanced chemical equation. We're going to figure out what precipitate is going to form, and then we're going to figure out what mass of the precipitate. So that's where we're going to stop. We're going to try to stop at mass of the precipitate. So step number 1, we're going to write out that balanced chemical equation. We've got our sodium phosphate and our lead nitrate. They're going to react to form sodium nitrate and lead phosphate. We look at that. Right, looking at this lead, I got 3 leads over here on the right, only 1 lead on the left. It's not balanced. I need to balance this guy first. Right, so I've got to balance it with the appropriate coefficients so that everything balances out. I've got 3 leads and 3 leads. I've got 6 sodiums. I've got 2 times 3, 6 sodiums. So that's all balanced out, right? The next thing we need to do is convert everything into moles. So I'm going to set up my little grid. And once I've done that, I'm going to look at my 2 amounts of moles of my 2 reactants. Right, for my sodium phosphate, 0.003 moles. So I write that under my sodium phosphate. I can put a big X over underneath my lead nitrate because we're going to assume that's in excess. And then I figure out how many moles of my lead nitrate. I take my volume of lead nitrate times my concentration of lead nitrate. And I get 0.004 moles. I'm going to write that down underneath the lead nitrate, and I'm going to put a big X under the sodium phosphate because we're going to assume that's in excess. Right. Now I'm going to use the balanced chemical equation and my stoichiometry to see which one is the limiting reactant. So I will take my 0.004 moles of my lead nitrate, and I'm going to figure out how many moles of lead phosphate I'm going to make. This is a 3 to 1 ratio. It's a 3 to 1. So I'm going to end up with 0.00113 moles of lead nitrate from my 0.004 moles of lead nitrate. Is going to give me my 0.0013 moles of lead phosphate. Now I'm going to do the same thing over here with my sodium phosphate, and I'll see how much of my lead phosphate I can make. That is in a 2 to 1 ratio. So I'll get 0.0015 moles. If I look at the two, the one that's going to give me the fewest number of moles is my limiting reactant. So my lead Nitrate is going to be my limiting reactant because it's the one that produces the fewest number of moles of product. I've got my moles of product. I'm going to bring that guy up to my mass level up top. And I'm going to use the molar mass of the lead phosphate, which is 811 grams per mole. So I take my moles, multiply by my molar mass to give me grams, and I get 1.05 grams of the lead phosphate precipitate. Right, so the setup here, once we did our balanced chemical equation, we realized what our spectator ions were, right? We were only concerned with, like, how do we do this as a regular old limiting reactant type of problem, right? Now, I'm still going to have stuff left around. That would be a good follow-up question, like, what is the concentration of the remaining sodium in solution, right? So if I had to do that, right, I'd figure out how many moles of sodium I had. Right, 2 times, I've got this many moles of my sodium phosphate. I would take this 0.003 times 3, and then I would need to divide that by the total volume, 10 milliliters and 20 milliliters. Right, so it gives me a total volume of 0.03 liters. Right, so that would be a good follow-up question to kind of do. If you want me to do one of those in office hours, I will gladly do that, or we can do that in class sometime. So feel free to ask. Right, so let's do another concept check. If we've got 10 milliliters of 0.3 molar solution, what is the concentration of the nitrate ions left in solution? Right? So it's basically the same thing. What's going to happen to our nitrate ions? So let's go back a page. Right? We look over here. Right? We've got all of these nitrate ions in solution. How many nitrate ions do we have? Well, if our concentration of the lead nitrate was originally 0.004 mole, if I originally had 0.004 moles of lead nitrate in here, right? My nitrate ion concentration is going to be twice that because it's lead nitrate. All right, so we take our original number of moles of lead nitrate. We look inside the molecular formula at that internal stoichiometry. So there are 2 nitrates for every mole of lead nitrate. All right, that's going to give us moles of nitrate. We then need to get the concentration. We need to look at the volume. So our volume is going to be the sum of the 2 volumes, right? So we're going to take 10 milliliters plus 20 milliliters is equal to 30 milliliters. And then we'll real quick convert that into liters because there's 1,000 milliliters per liter. And it's going to give us 0.030 liters, right? So we've got this many moles. Right now we're at moles. And we're going to figure out a concentration. Concentration in units of molar is moles per liter, so we just need to divide that by 0.03 liters, right? And we're going to end up with 0.008 moles of nitrate in 0.03 liters of solution. And that's going to equal 0.266 moles per liter, or 0.266 molar. So that's how much nitrate ion is left in solution in terms of moles per liter. That's our concentration. This is the other follow-up question, is how much phosphate ions in terms of moles per liter is left over when we're done. So in order to do this one, we need to figure out how many moles of phosphate was used, and then we're going to figure out how many moles of phosphate are left over. We'll then convert that into moles per liter as our next step. So our plan is going to look like this. Our moles of excess phosphate are going to equal our moles of original phosphate that we started with minus the moles we used. From our volume and our concentration, we know that we started with 0.003 moles of phosphate. We then need to look at our balanced chemical equation to figure out how many moles of phosphate were consumed. We can go back to the grid we'd set up before, and we already know what the concentrations and the number of moles are for each of our reactants, and we know which one is our limiting reactant, so we're going to plug that in. And we can pick either the limiting reactant, or we could pick the amount of products that we formed. It doesn't matter. We can draw the arrow and look at the stoichiometry either way to figure out how much of the sodium phosphate we would have consumed. I'm going to go with this PB over here, right? Or I could go with this one. I'm going to go with this because I've already got the number, and the number's a little easier to figure out, right? So I'm going to get the same answer whether I pick the blue guy or the green guy. I'm just going to pick this because it's got a coefficient of 1 over here. Makes my math a little easier. So going from our product, it's a 2-to-1 stoichiometry. So I'm going to have twice as many moles of the sodium phosphate consumed as lead phosphate produced. So I'm going to end up with 0.00266 moles of my phosphate that were used, right? So this is the amount of phosphate that was used, right? The amount of phosphate I started with is up here, right? The 0.003 moles up here. All I've got to do is subtract to find the difference. So 0.003 minus 0.00266 leaves us with a remaining 0.0003 leftover moles of phosphate. I then need to convert that into concentration, so I'm just going to divide by the volume. Again, our volume is going to be the sum of the two volumes we used. Our volume will be equal to 10 milliliters plus 30 milliliters, or 0.03. I take my leftover moles of phosphate, I divide by the volume in liters, and I end up with the concentration of 0.0113 molar leftover phosphate, which by weird coincidence is what we get for the amount of lead phosphate that's formed. All right, so see how we did this, right? We're using our balanced chemical equation as a way to get at the stoichiometry and the mole-to-mole ratio between our reactants and our products. Right? Sometimes we're going from products back into reactants like we did here. Right? We're almost always going to go from reactants to figure out what is our limiting reactant. Right? We'll figure out how many products we're going to form, which is the smallest amount of products we're going to form. Once we know that, we figure out how much product we've got, what our limiting reactant was. We can figure out how much of our excess was used. If we know how much of our excess was used, we can just subtract to figure out how much is left over. And then if we need to, we can convert that to another unit like concentration or grams if we needed to do grams. Here's another example. All right, so let's calculate the mass of solid sodium chloride that has to be added to 1.5 liters of 0.1 molar AgNO3 solution to precipitate all of the Ag ions in the form of AgCl solid. All right, so you see this, right? And the first thing you ought to be doing is step 0, write out your balanced chemical equation. All right, it's going to be sodium chloride and silver nitrate. It's going to make AgCl solid and sodium nitrate. I look at that, it's already balanced. We can probably get rid of the spectator ions, right? Our sodium's not going to show up, right, as anything other than a spectator ion. Our nitrate's not going to participate. Those guys are always going to be soluble. So our net ionic equation is really just Cl minus and Ag plus, because it's AgCl solid, and that guy's already balanced. The other thing you're going to want to do is, here I've got a volume and a concentration, and as soon as I see that, I'm going to get moles, right? I'm going to take my 0.1 moles per liter. I'm going to multiply that by my 1.5 liters, right? And I'm going to end up with 0.15 moles of Ag plus, right? So that should be part of your basic setup. There might be times when you got extra information and you're not going to need that, but just as a reflex, balanced chemical equation, if you see a volume and a concentration, put it in moles. If you see a mass, put it in moles. Right? So this is what we're going to start with. Right? They're just hiding the moles in here. Right? It's going to be like playing whack-a-mole. Are they hiding the moles as volume and concentration? Are they hiding the moles as grams? Did they hide it as number of atoms? Get it into moles. Have I mentioned getting it into moles is really important? It's really important. Right, so our objective, we want to find the mass of solid sodium chloride. All right, so we want a mass of sodium solid chloride that's going to react and get rid of all of our AgCl. We do know that we've got a volume and a concentration of silver nitrate, right? So we've got this as a given, right? We're going to figure out the moles of Ag in solution. So we're going to determine the ions present in solution. We got silver and nitrate and sodium and chlorine, right? And that's going to be our guys in solution. We do not have to worry about the sodium and the nitrate. They're just going to be spectator ions. All right, step 2, we're going to write out the balanced chemical equation. This is our net ionic equation. And right? And then we're going to determine the moles of Ag present in solution, right? Why I already said to do that is like you should do that by instinct and autopilot. 0.15 moles of Ag plus, right? So now we got our moles. Next, we determine the number of moles of chloride ions required to react with the Ag. They're going to react in a 1-to-1 ratio. So 0.15 moles of chloride are going to be required. So 0.15 moles of NaCl are required, right? So again, if you wanted to do it my way and set up the little equation like that, right? You could do it that way. And then you can do like the moles level down here, and we figure out the moles. We've got 0.15 moles of AgNO3. We're going to go back and go this way to figure out how many moles of sodium chloride we need. It's a 1-to-1 stoichiometry, so I'm going to write the little ratio up here, 1-to-1. 0.15 moles of AgNO3 are going to require 0.15 moles of sodium chloride. I can then convert that back up into mass using the molar mass of sodium chloride right up top. I'm going to have my grams level. So I'm going to use my molar mass of 58 grams per mole. And I'll end up with 8.77 grams, right? Whether you do it sequentially or whether you use this little grid method like I'm going to use, doesn't matter. As long as you're ending up at the same place, you're fine. Acid-base reactions are another type of reaction.